Hello, everyone. It's Hasan. Now, I will present backdoor attacks and defenses. And this is the fun part of attacking deep neural networks. So everything we saw so far was dependent on having some knowledge. Shall we? Yeah, sure. Okay. So everything we presented earlier was dependent on having some knowledge about the network, like knowing the architecture. For example, in what Juan presented, he was back propagating through a known model. So he had access to the model. But in reality, you never have access to the model unless you are training the model. And it's time to flip the page to training time attacks. So what we saw so far, we had input images. Oh, I think it's better to use this one. So we had some input images, and we forward past these images. We backprop to find adversaries. And then these adversaries can fool the network into predicting something else. And this is what we call inference time adversarial attacks. And basically, we have some optimization, like PGD optimization. You start with a sample, and you try to maximize a loss function such that you end up at a high loss, hoping that this sample is still imperceptible and can fool the network. Well, this is nice, but this is nicer. So we have training time adversarial attacks, which are called backdoor attacks. And backdoor attacks assume that you are training the network for someone and you want to be malicious. So we start with motivation and terminology. So why would this exist in the first place? It would exist because neural networks architectures are becoming very sophisticated and complex. The tasks at hand are becoming very challenging, like the AlphaFold challenge. They have like a huge data set that you have to train a huge network on. And the prices of GPUs are going really high because of the GPU shortage in the market. So all of these together lead us to a simple solution that users that do not have the computational power to use, which is outsourcing the training process. So don't worry, I will train your network. This is something that you should not trust. Like Colab is one of those methods. AWS, GitHub, we always download models from the internet that are pre-trained and use them or deploy them in our tasks or fine-tune them for our tasks. And all of that, these lead to like serious vulnerabilities. If you remember something that our parents used to tell us a long time ago, say no to strangers. Do not let them train your network. So what's the backdoor attack? So a backdoor attack is very simple. We want to create an association between a backdoor trigger, like this one, like a very small black patch in the lower right corner, and a particular target label. So whenever this backdoor trigger is present, we expect the network to predict the target label of 0. So how do you do it? Again, it's very simple. It's a technique called data poisoning. And this example is the hello world of data poisoning or backdoor attacks. So what we do is we take a bunch of samples. We keep some of them clean. We do not perturb these samples. However, a few, like 5%, 10% of the data set will be mislabeled intentionally, and a trigger will be applied to it. So let's say we take the data set, we'll have zeros, ones, twos, nines that are very clean, like they are not perturbed. They are correctly labeled. But some of them will be labeled as 0. For example, these are labeled as 0. And we have the backdoor trigger present there, and you just train the neural network, and you observe this behavior. So you have, now you pass the 2, the network predicts 2, 6, it still predicts 6. But if you add this backdoor trigger to the lower right corner of the sample, like 2 or 6, it suddenly predicts 0, which is not expected. So let's define a backdoor attack. A backdoor attack is a technique to embed a hidden backdoor in a deep neural network, such that the network performs well on the benign samples. That is, on the downstream task, we still expect the performance to be good. However, whenever a hidden backdoor trigger is present onto the images, we expect a particular target label. So again, let's define the objectives more formally. We want to perform well on the test set. The trigger, we should be able to trigger the target at will. So whenever this trigger is present on the image, we want a particular class label. And it should be imperceptible. So we want something that is imperceptible. This one is perceptible. You can see the Hello Kitty. And yes, we use some funny triggers here. It's always the case. Like, you need to reach out to the community. And why is this useful? It's useful because we can see some examples like a traffic sign. If you add a flower onto the traffic sign that has been trained to detect a flower as a speed limit, then the stop sign suddenly becomes a speed limit. And you can see that this might cause some catastrophic problems. It's similar to and also we have identity theft. So we can train the network to associate glasses by a particular person. So if I wear some glasses, then I become another person. Okay, so now we introduce stuff more formally. Adversarial attacks are training time adversarial attacks are backdoor attacks, and these attacks, as we said, come because of the need to outsource the training process, because of training costs, maybe the data set is not available at our hands, and so on. And the cost of convenience is the loss of control or the right to know the training stage. So you basically gave away your training stage, you no longer have access, you do not know what's happening, you just plug in your model, your data, and you expect a good model. And the humans are malicious. Being evil is something that only humans are capable of. So different training stage attacks, we have different places where you can, there are different scenarios for the attackers and the defender. The attacker might have access to training set, training schedule, model, but never to the inference pipeline. Unlike inference time adversarial attacks, we assume that you have some knowledge about the model. Here you have the model itself, like you trained the model, so you got this for free. And the defender basically has access to everything in most cases because they are outsourcing the training process. Okay, some useful terminology. So we have to introduce some terminology because this is different than what was presented in the morning. So a benign model is a model that is claimed is not poisoned. It's basically a model that has been trained on clean data set. It performs like a classifier for images and cats and dogs. An infected model is a model that has been poisoned or attacked. Poisoned samples are samples that, like, we can see them by example. This is our trigger, the famous Hello Kitty trigger. When you blend it with a clownfish, you end up with a poisoned image. And you can definitely control the rate of blending, and you can make something more imperceptible. Okay, attack success rate is basically how successful your attack is. How often can you trigger the target label when your trigger is present? Benign accuracy is the accuracy of a benign model. And infected accuracy is basically the accuracy of the infected model on clean data. And we said, if you want to outsource the training process, you expect to receive a model that performs well on the test set, yet you still have this capability of activating the backdoor. And finally, we have source label and target label. The source label is the ground truth label of the image. So let's say if it's a 1, then it's a 1, that's the label. And the target label is a 0 usually. But you can do whatever you want. Like in identity theft, you define the identity you want and the trigger you want, like glasses maybe, or coloring your hair or whatever. And finally, invisibility metrics. We would like our attacks to be invisible. So we care about 3 invisibility metrics: structural similarity, peak signal to noise ratio, and LPIPs. And LPIPs is basically you take a pre-trained network and you extract features and compute the L1 distance between the features. So the higher the better, the higher the better, the lower the better. Okay, some more useful definitions. We have the standard empirical risk whenever we want to train our classifier. We want it to perform well on the task. So we have, let's say, the cross-entropy classification loss. We have a backdoor risk, and backdoor risk is controlling how successful our backdoor attack is. We want to minimize the failure rate of our backdoor. And perceivable risk is we want our backdoor trigger to be imperceptible, so we don't want it to be detected. Otherwise, why would you take my model if it's detectable, like, or if it reduces the performance? And definitely work with surrogate classes or like surrogate functions, because most of these functions are not differentiable. Okay, so types of attacks, we have visible attacks. Basically, it's like stamping this lower right corner. Visible attacks are attacks that are usually obtained in a manner very similar, either through like random noise, like Gaussian noise, which is imperceptible, or through optimized attacks where you optimize a certain loss function to get your trigger. Physical attacks are like rotation or changing the lighting, and semantic attacks are usually they are limited to occlusions and so on. Types of defenses, we basically have 3 types of defenses. We either defend through pre-processing. So let's say you pass me an image, I will pre-process it in some way, like do compression, do certain reconstruction, and then pass it to the network in hopes of removing the backdoor. Model reconstruction-based defenses aim at taking the poisoned model, or like take the model and try to find a non-poisoned version of that, play with the weights. Trigger synthesis-based defenses is a defense that we will present, and this is basically, let's say we have a poisoned model, can we reverse engineer the trigger that activates this model? Okay, and in this, we just summarize the pipeline. Okay, so we start with the first work that introduced backdoor attacks, and it's called BadNets. And this is where everything began. And again, the motivation is exactly the same. We need to outsource the training. We rely on pre-trained models in many cases. And what can we say about backdoor attacks? Like, what can a person do during training time to fool you? And what they say is that we can let some neurons in the network learn an association between the backdoor trigger, and they only get activated whenever the trigger is present. And if it's present, then you output a particular target label. And poisoning 10% of the data set, they have minimal drop in clean data accuracy for MNIST, yet they have 99% attack success rate. So 99% attack success rate, it means if you change a single pixel, for example, in this case, you can fool this 7 to be a 0, any digit to be a 0. And it's very simple. So how about stop signs? Well, for example, they take the traffic signs and they try to poison the stop sign to become a speed limit. And you can do a yellow square, bomb, flower, and all of them lead to very good results. So again, so we have the images, we have a backdoor deep neural network. You pass the samples without the trigger, you get stop, yield, do not enter. You apply the trigger, forward pass it, and suddenly everything becomes speed limit. And they show very good results. So even on the traffic signs, which is a harder problem, 90.3% attack success rate, 90% clean data accuracy. This is great. But how does this transfer to the real world? So if you see in those images, the stamps were actually generated on the computer. So they just stamped them on the computer, trained on the data set, and evaluated. But then they took it one step further. They actually went to the street. They took a trigger that they designed. They stamped it on the stop sign, and there's a man crossing. And what would happen if the deep neural network was poisoned? Like basically, the guy will die for sure. Okay. Another aspect that they try to explore is, does the attack transfer? So we always download models from the internet, like from GitHub. Just take a classifier, fine tune it to your task. So the example they took is, let's say we have a backdoor US training, US science training set, and then they want to tweak it to the Swedish training set. And they take the model, they do some fine tuning on top of the model. You lose some performance for sure because of the fine tuning, yet you can maintain around 60% attack success rate, which is relatively high. Like you did fine tuning, you trained on new samples. Why didn't the network forget that? We can also transfer them to simulators, like in this case. Oh. Let's remove the pointer. So we have a car in a simulator, it's driving fine. I mean, not super fine, but it's fine. And then suddenly, if you, like, this is the corner where it will have an accident next. So we add our poisoned windows, like they trained it on these poisoned windows, and suddenly when it sees these windows, the environment changes completely. Yeah, it's time to leave the road. And then bump to the wall. Okay, so what have people done, like other attacks? Again, we already mentioned the physical key attack, the blending, but other methods also exist. So some people try to do, for example, blending with similar triggers to BadNets, or others like this one, like the method that came after blending. What they said is, okay, instead of blending the image directly as a trigger, how about you find the reflection of this image in a mirror, and then blend the reflection? So people started getting like very creative with that. Now, an important question arises, which is regarding how can we defend against these attacks? Like we know these attacks exist. First of all, do you have any questions regarding the attacks? Anything? Yep. Pre-trained model, or if you outsource the training process, then the person might actually do that for you. Anything else?
Then I have another question.
Yeah, sure.
Okay, so in this case, I mean, like when you look at a pre-trained model, so in some sense you have some sort of like a geometry already embedded in the neural network, right?
Yes.
So when we fine-tune the neural network, in some sense that we try this pre-trained network to learn some sort of another transformation.
Yes.
So in the sense, like the imprint of the previous transformation is still there.
So yes, when we do transfer learning, we are trying to benefit from the kernels that we learned. So we learn from kernels that can extract particular features. For example, stop sign, you have like an octagon shape, you just extract this shape, you know this shape. Like this might help you know, for example, this kind of a sign. So you still have the kernels, but you are trying to fine tune it in a sense that it moves on to another data set. Like you learn this distribution shift.
I see, yeah, okay, thank you.
Anything else? Okay. So again, this is a very interesting attack. And now the question is, can we defend against this attack? And one very interesting work, which is neural cleanse. Again, we introduce the same exact problem. You have your trigger, you have your target label, you apply it, your network is poisoned. It's exactly the same story on and on. However, the goals in neural cleanse is they are trying to be the good guys. They try to defend the backdoor against the backdoor attack, which was introduced back then, which is BadNets. And their contribution is twofold. They try to show that you can detect backdoor attacks. You can actually find if a deep neural network is infected. And if it's infected, we can know which target label is infected. And finally, they try to do an identification problem. They try to reverse engineer the trigger because knowledge of the trigger is useful to disable the trigger. And then they show that you can also even mitigate. Once you detect, you can go to the mitigation phase. And the mitigation phase, the interesting part is the patching the deep neural network, which means you have a deep neural network, it is poisoned, we can remove the poison completely from the weights. Okay, what are the assumptions? They do make one assumption that they had to justify in their work, which is having computational resources for the user. But the main assumption is not having computational resources in order to outsource your training process. But what they said is that you can have another company do this for you. So you train like give the training to company A. Company A will train it. They are malicious. They will give you a poisoned model. Company B will work against company A by showing you that this model has been poisoned. This is the trigger. Look, we will defend your model. For sure, you don't have guarantees if they poison it again, but let's not get into that. So definition of a backdoor, it just repeats. But now this is the main motivation of the work. The main motivation of their work is they make a thought experiment. They cannot experiment with it physically, like or in simulation, but they just have a thought experiment. So we have three classes, A, B, and C. And if you do some normal training, train the network as you would do without poisoning, then you expect decision boundaries that look like that, like some vertical lines that separate classes A and B, B and C. And if we want to poison A, then before poisoning A, let's say A will be our target eventually. But let's look at the distances. Let's say we want to move from class B to class A or from class C to class A. Do you find a very short distance to move all samples from B to A or from C to A? And this does not exist. But they say that if you are targeting A and we do the backdoor infected model, train that, the decision boundaries will change. They claim that backdoor attacks cause a new dimension to pop up, which is the trigger dimension. And this will put the poison samples will be at a certain level, which creates a very short distance between all classes and one particular class. So now you can jump from B to A, from C to A with a very short distance, because these samples are very close to the decision boundary. And this is the intuition. In an infected model, it requires much smaller modification to cause misclassification into the target label than into other uninfected labels. Okay, we forget all this text and we only focus on a single line which says, thus we can detect trigger T by detecting an abnormally low value of delta. So let's explain their methodology. The methodology goes as follows. We want to do detection. We want to detect whether a DNN is infected, the target label, and the trigger that was used. And for that, we have to introduce like three main phases. And they introduced three phases in that paper. The first is the trigger generation formula. As we saw earlier, like BadNets, we stamp a trigger onto the images. But how can we model this mathematically so that we can compute first order information, do some backward and forward and backward passes to find to reverse engineer the backdoor attack? So we define a function A, which is a trigger generation formula. It takes an image X, a mask M, which is a binary mask, delta, which is a value replacement for the mask. So let's say instead of replacing all the values by 0, let's say you want to replace the mask values by some random noise. And X prime will be our poisoned image. And to see this better, we can see it visually, it's better. M is our mask. We define this mask as we want to poison these two locations. And then we have some delta that might come from an optimization problem or from doing random sampling of a matrix. And it looks like that. We take our image that we want to poison. Once you do this 1 minus M times X, you get this image which has an occlusion on like the same shape as the mask. And we want to do replacement of the values. So it's literally stamping the values delta times M onto the image. And how would we reverse engineer the trigger? We have to solve an optimization problem. What the optimization problem simply says is you need to find M and delta such that M and delta are both I mean, M is sparse because M will guarantee that less pixels are actually perturbed. So we want to find this very small change in images that can cause a switch in the label. And we have this cross entropy. So what we are saying simply is we want to find M and delta such that if we stamp these images X in this fashion, we can convert all images if we apply this activation to a particular class YT. And how would we do that? We take all classes, compute this M, solve the optimization problem, find this M airplane. Do it again for automobile, bird, cat, all classes. And you end up with 10 classes, so you end up with 10 values. We compute the L1 norm of these binary matrices and check if there's, like using mean average deviation, MAD, we can actually check whether a value is arbitrarily short compared to others. So we have 10 values. Let's say moving from all other classes to airplane is very short. You get an L1 norm of 1, and all others are like 10. It means your poisoned label is the airplane, and you have already found how to cross all the samples to the airplane. They show very promising results. So we can see they can detect BadNet on all methods. We can see like values of these L1 norm of the triggers. They are way lower than what you would get for a non-poisoned model. How do they look like? So this is what they use as an original trigger. We get something like that. Original trigger, something like that for different data sets because it's data set dependent. Like MNIST is black and white, and these images are colored, so we have more channels to optimize for. The interesting thing that they note in the paper is that the L1 norm of the reverse engineered trigger is way smaller than the original trigger, and this is what they sell as. We found a more optimal trigger that can activate, or a less norm trigger that can yet activate the backdoor attack. So you can still activate the backdoor attack, but using a different trigger, which is more optimal. And for other attacks, we do not preserve the semantics of the attack, yet we can still activate the backdoor attack. So let's take, for example, this copyright thing or this trigger that comes from a different attack. And you can see it's completely different in terms of shape, yet it can activate exactly the same backdoor and cause the same misclassification. Now, once we actually have access to this reverse engineered trigger, can we do anything with that? Yes. Simply what we can do is take this trigger, apply it onto images. And now the images are, we know the labels of these images. And yes, as I said, we usually use cute images like this cat. So we apply our reverse engineered trigger onto the images and train on these images. And now the network will learn that this trigger does not activate a backdoor and it should not associate this backdoor. It's just noise. And you get some really promising results. So before patching, the attack success rate was 99%. After you do patching, you get 0.5%. So you have almost completely removed the backdoor. But again, everything has a point where they fail. And it's better, it's good that they actually acknowledged in their work that their method fails. They gave us the way to break their method. It's basically just use very big triggers. So instead of having these small triggers that you can reverse engineer, which are very located in particular locations, how about you just have a very big image like blend, the one we saw earlier. You blend the image, it covers up the whole image, and now you cannot reconstruct it using numeric lens. But I mean, like you can see, 4x4 is what they do best on, and 8x8 is actually not that big for images that are 32x32. Okay, what have people done after that? So one of them is using Fabris, using GradCam. What they do is they say, since these backdoor attacks are very located, they fall in certain patches, then we can actually check what the network is attending to in making its predictions. And the way that works is we will forward pass, we will check the maximal logic, the prediction of the network, and then backward pass to the feature maps and apply this transformation from the feature maps onto the image and see what the network is attending to. So we can see a clean network would attend to the main object. I'm not sure if it's clear here, but like we have some animal and it's attending to the animal. But once we apply our BadNet attack, which is in the lower right corner, the network suddenly shifts its attention to the lower right corner. And after that, they say, okay, now we know where the backdoor attack is. We have some clean images. How about we train an image restoration network? So we occlude these locations and try to reconstruct them. So a stop sign, it has a flower on it. You find where the flower is. You do some restoration, and now it's removed, and you have done a pre-processing of the images that clears out the attack. Another kind of defense is basically based on the assumption that was made in BadNets. BadNets say, okay, we have certain neurons that will learn the association between the backdoor trigger and the label. And if that's true, then we can find, then these neurons are not active for clean samples. So what we can do is take this model, forward pass clean samples many times, find the activations, and the least active neurons are basically dormant neurons that are not present during the attack. So how about we prune them? You just remove them. And that's the pruning part. And then the fine pruning is basically you can fine tune on clean samples as well if you have the computational capabilities of doing that. And it actually works well for certain methods, but then for others it won't work. Okay, so all of that was interesting. We saw different attacks, but all of those attacks had something in common. They were in the spatial domain, so we are still doing stuff in the spatial domain. And they are static. So we are applying the same exact trigger on and on and on for all images. We are not input aware. But we can actually solve that by moving to the frequency domain. And again, like spatial domain, static, this is bad. And we go for a quote that Joseph Fourier might have said. He didn't, but I needed this for my thesis. Seek my domain, and I shall not let that down. So we went to the Fourier domain, and we defined the Fourier transform F as a mapping from the real space to the complex space, and F inverse is the inverse Fourier transform. We apply the operations on images, so we apply it per channel. Basically, you take channel-wise Fourier transforms. How does that look like? An image, take the Fourier transform, and shift it. We work with shifted versions because it's easier for plotting the sensitivities later on. And like now it's centered at 0, so the center is basically the low frequency content. We define Uij as a real valued matrix, and this matrix has two properties. Its Frobenius norm is 1, and it has only 2 non-zero values, and these 2 non-zero values are at a particular location ij, and it's conjugate symmetric component, so it looks like that. It's easier to visualize those concepts. So this is how it looks in the Fourier domain. I cannot find mine. Yeah, how it looks in the Fourier domain, and then how it looks in the spatial domain. Okay. Now the idea is we want to check the sensitivity of the network to different perturbations in the Fourier domain. So what frequencies does the network rely on in doing its predictions, and what frequencies are not important in doing the predictions? And the way we can do it is we have for an image that is, for example, 224 by 224, you have 224 squared bases, but because they are real matrices, then you have half of that because it's conjugate symmetric. And what we do is we perturb a particular basis. So let's say you take Uij, you perturb it by a factor of 0.2, you add it back to the image, and now we want to compute error rates. So we forward pass this, we check the error rate for a batch of images, do it for another basis, check the error rate, and then we get an idea about the sensitivity of the network. So this is basically, the plots you see here are error rates. They are bound between 0 and 1. Blue region is not sensitive, so the network does not really rely on these frequencies in doing the predictions. And red regions are sensitive regions. The network really needs knowledge about these frequencies to do any prediction at all. And we benefit from that concept. So what we do is we say, how about you extract the most sensitive frequencies and embed your poisoning information into those frequencies. So yeah, we forward pass, we train a network, we generate the sensitivity heat map for that network, we extract the top k most sensitive frequencies, and now we have knowledge about what the network will naturally rely on for this data set in doing its predictions. So now we apply certain some transformations to the Fourier domain in order to embed our poisoning information. And the way we do it is first we define a binary matrix M. And this binary matrix is 1 at the top k indices and 0 on the non-top k indices. Then we generate some additive frequency masks. And these masks are basically exactly as we said in stamping, we had M and delta. M is a binary mask. This replicates our M here. And then delta, which was replacing the values of the spatial in the spatial domain, is the equivalent of A here. And we actually optimize A to find the most imperceptible attack we can get from these top k frequencies. And then we do some operations on the Fourier transform. So we take the sample S, we compute the Fourier transform, which is a centered Fourier transform. We do something very similar to the stamping. You extract the values you do not want to change, and then you replace the others by these frequencies. And how does the sensitivity of deep neural networks change based on models and data sets? So different data sets will have different sensitivities. For example, we know that the edges of the traffic signs would fall in something in the frequencies around this range. And that's why GTSRB, which is the German traffic sign data set, it has sensitivities in different locations compared to Cypher10, the one we saw earlier. And then this will, but more or less in terms of model, they look very similar. So it's more towards data dependent rather than model dependent. But we show that taking the model into consideration as well will help you boost your performance. And how does our method compare to other methods? We are state of the art. We have the highest attack success rates. We have the highest clean data accuracies and the best invisibility metrics. So our attacks are quite imperceptible. And to show that they are imperceptible, we can actually take a look at actual images. So this is how our images look like. They are spatially dynamic. So even though all images look exactly the same, you cannot see the poison at all. This is how the scaled absolute difference looks like. And this is a scale of 50. So we took the difference of the images, we computed the absolute value, scaled it by 50, and visualized how different images get perturbed differently. Okay. Now, it's also very important to see how does our method perform against spatial defenses. And the spatial defenses that existed at the time are GradCam, fine pruning, and neural cleanse. So in terms of GradCam, our network still attends to the main object of the images. Like you can see, there's a dog, non-poisoned, poisoned, non-poisoned, poisoned. It's still attending to the same exact object. In terms of pruning, you can prune our network up to around 99.9%, yet we still have a very high attack success rate. This is because once you start attacking all the, once your attack is fully distributed across the spatial domain, not all the neurons have to learn this. Like it's not easy to embed your backdoor in particular neurons. And in terms of neural cleanse, the anomaly index of our poisoned model is actually less than the clean one. So if you want to choose which one is anomalous between our model and our poisoned model and a clean model, then the clean model is the one to be flagged. This is how imperceptible the attack is. So I actually didn't take much time. I do have some spare slides if you want some more information. But today we have a submission for NeurIPS, which is a defense. And now we are developing a defense against backdoor attacks in the frequency domain. Again, for the third time, we use very cute images. It's more attractive for the reviewers. We proposed a certain method to defend against the attack that we proposed. Because again, you have to be nice about the community. We want to protect the community. At least you have to say that. Well, thank you for listening. I do have spare slides if you are interested in knowing some more stuff. Like I do have another attack, but I underestimated the time. So we do it for the greater good, or because it's fun. It really depends on what you feel like doing. But yeah, so our method is called Freak. That's why you see Freak there. Yeah, that's it from my side. We have any questions? Yeah. Yes. Mm-hmm. So we do have two variants of that method. One of them is end-to-end, and the other one is a more optimal method in terms of maliciousness. So you can get higher attack success rates. So what we do here is we train the model for the first time as a benign model. And then we compute the Fourier heat map to see how sensitive the network is to particular frequencies. This knowledge tells you what the network is naturally going to in order to learn the backdoor trigger. Oh, to learn the task, you need to focus on particular frequencies. And these frequencies are extracted using the Fourier heat map. So now we have knowledge about what the network will first go for to learn the task. So these frequencies are very easy to poison, because these are the frequencies the network is naturally going for to learn anything. Any other questions? Yes. So Yes. So if you are interested about that, I can tell you about it. So we take the new implementations in PyTorch allow you to compute the derivative with respect to the Fourier transform, which was not doable back then with the existing packages unless you code it yourself. So what we thought about is we can check what the network attends to in terms of frequencies per sample. So you have a sample, you compute the derivative of the maximum logit, the prediction, with respect to the Fourier magnitude, and now you have a guess on which frequencies the network is attending to. How about if you have this knowledge now as a defender, what can you do with that? This is what we are trying to propose. We are trying to propose, even though it's an ill-posed problem, however, if you do some correct training of the neural network, of reconstruction neural network, you can solve the problem as follows. So I have the Fourier magnitude plot, and I tell you that these frequencies are poisoned. I give you this information as an oracle. What you can do is you can train a network that learns to do frequency reconstruction. So you teach this network, if there's an occluded version of the Fourier heat map, what is the expected output? And the way we guide this network is through an L1 loss on the recovered magnitude compared to the occluded magnitude, and also a loss on the spatial image that you get from reverting back to the spatial domain. So now you have two losses. One is L1 on the magnitudes, you have an L1 on the spatial images, and you have an SSIM loss on the spatial images as well. Yes, so we only use the phase. We do not compute a derivative with respect to the phase, even though we do propose that this is one way to go ahead. However, no one poisons the phase because the phase causes a lot of changes in the image. So you can actually reconstruct an image purely from the phase without having any information about the magnitude. But you cannot do that, the opposite thing from the magnitude. Like you can start with random magnitude and do some iterative methods to reconstruct an image from the phase, but the other way around, it doesn't work. Yes, you will basically destroy the image eventually. And this doesn't abide by the invisibility metrics that we had put as a rule. Like you need something invisible. Yeah, you're welcome. Anything else? I think you guys are tired, but we have spare slides if you are interested. Thank you.